Yes, so hello everyone, and welcome to this week's SETS online webinar. I'm Ola, and I'm talking to you from Newcastle upon Tyne in UK. And the first thing, as always, we would like to thank our sponsorship from EIS, which allows us to offer all of these resources free of charge. So our resources include recorded lectures, learning tools, and virtual field trips. And please make sure that you will check our website. One last thing before I will go to our speaker, the Carbonate Forum 2022 will be held on the 10th and 11th of May. This is Tuesday and Wednesday. And again, please check Twitter feed for information about the Carbonate Forum. Now, our today's speaker is Romain Vaucher, and he has a master from University of Geneva and a PhD from the University of Lyon. His postdoctoral work has taken him to Argentina, to Canada, and to Taiwan. And presently, he's a researcher at the University of Lausanne. Romain is an expert in clastic shallow marine environments and works on both modern and ancient sedimentary systems. And that's the thing he will be talking about today. So without much further ado, Romain, the stage is yours.
Thanks, Ola, for the nice introduction, and thanks SETS Online for organizing this webinar. Really appreciate them, and thank you very much for inviting me. So today I'm going to present you what we did recently in Taiwan, more specifically related to sea level and sediment fluxes. So let's first looking at climate cycle. So this curve is probably one of the most famous curve in paleoclimate studies. So here you get the time here in the delta O18 of benthic foraminifera, and what we can see on this curve is like we have a strong cyclic signal of the delta O18 of the benthic foraminifera. And the delta O18 of benthic foraminifera is super useful as a proxy for ice volume, because when we have higher delta O18 value, it implies that we have a low temperature and then lower sea level, and conversely, when we have lower delta O18 value, we have higher temperature and then higher sea level, and then these cycles are translating glacial and interglacial period. For the late Pliocene, early Pleistocene, and we actually have an orbital forcing linked to the obliquity, and during the late Pleistocene, it's mostly influenced by the eccentricity. So just a little reminder of what are the astronomical parameters of the Earth, so-called Milankovitch cycle. So the eccentricity actually describes the shape of the orbit of the Earth around the Sun, which is evolving from a more cyclical to a more elliptical shape. And this has an influence on the annual global insolation received on the Earth, but its more important influence is on the precession cycle that we're going to see later. Second parameter is the obliquity, the tilt of the Earth, and this has a strong influence on the insolation received at high latitude. And finally, the third one, the precession, which is a wobbling of the Earth, is actually responsible for the seasonal distribution of the Sun. It has a strong influence on hydrological cycle, especially at low latitude. So all of the three are acting at the same time and are a strong influence on the climate of the Earth. And as you can see here on this illustration, so each curve represents a spectral analysis of the last 1 million years, and what we can see on the eccentricity as two main periods, one at 400 and one at 100,000 years. The obliquity as the main period as 401,000 years, and the precession as two main periods at 23 and 19,000 years. And as you can see here, this curve is the insolation received by the Earth. So the insolation is the amount of solar radiation. And as you can see on the pattern, the insolation is mostly driven by the precession. As you can see, the similarity between the two curves. And actually, there is a modulation of the eccentricity on the precession index, as you can see on the pattern. And we also have an influence of the obliquity. Now, if we get back to the paleoclimate curve I presented at the beginning, and we look at what's occurring more recently in terms of climate change. So on this graph, it's representing the temperature anomaly versus time for the North Atlantic. And if we plot the temperature anomaly against the power dissipation index for tropical cyclone, so the power dissipation index of tropical cyclone take into account the frequency and the strength of the tropical cyclone, what we can see is that we have an increase of the tropical cyclone frequency and strength with temperature anomaly. Another effect of climate change on tropical cyclones. So on this graph, on the y-axis, we have the translation speed of the tropical cyclone, and here is the time. So the translation speed of the tropical cyclone is not the speed of the wind, but the speed of translation of the motion of the tropical cyclone. So, and what we can see is that we have a slowdown of the translation speed of the tropical cyclone with time, so linked to the anthropogenic warmth. And here on this graph, we show like the distance to the equator according to time. And what we can see is like the tropical cyclone are getting farther and farther from the equator, reaching more pole world environment. So this implies that because of the global warming, we have the tropical cyclone are covering a greater area, and then we then have a more important precipitation for a given area. So now if we want to understand what we're going to face, so we have to derive climate narrative from paleoarchive, and most of the paleoclimate studies are mostly derived from deep sea environments or lakes. And this is because both environments have high temporal completeness. The issue is like both the deep sea environment and lakes are not directly impacted by sea level change nor by extreme weather events. Otherwise, or shallow marine environment are influenced by directly influenced by sea level change and extreme weather events. The problem in shallow marine environment, so if we take theoretical stratigraphy for low accommodation and low sedimentation basin, so here we have the time, here we have the level elevation that we can consider as the creation of the subsidence in the basin, and we have a different order of climate cycle occurring on it. And what's happened is that the resulting stratigraphy from that is like a stratigraphic record of gap. As you can see here, most of the records, so what is deposited and preserved appear in blue, and what is white and red is all that has been eroded. So the problem with shallow marine environment with low accommodation and low sedimentation are usually poor climate archives. So what we wanted to do is to test the sedimentary record of shallow marine basin with both high accommodation and high sedimentation as climate archive. So for this, we went to Taiwan. So Taiwan is located right here between the East China and the South China Sea at the northern part of the Philippines. And so before Taiwan became an island, this area was mostly undergoing a rifting phase from the Paleocene up to the Miocene. And since the Pliocene, the dynamic here, or the geodynamic of the plate, inversed and start to subduct. So now we have a subduction of the Philippine sea plate beneath the Ryukyu Trench, and this is leading to a strong uplift of units, creating a flexure in the Forland Basin. And actually, the uplift in Taiwan are actually among the greatest uplift in the world. So these tectonic settings are creating the high accommodation in the basin. And now, if we look at its geography, so Taiwan is located right here in the northwest corners of the Pacific. And this graph represents a survey of tropical cyclone for the past 150 years. So each line is actually a cyclone, and where it's more red is where the tropical cyclone are the more intense. And as you can see, Taiwan is probably on the worst place on Earth in terms of tropical cyclone, and this is leading to a high sedimentation in the surrounding sea of Taiwan. And as you can see here on an example, so this is a Landsat view of Taiwan, so during fair weather condition, and this was just after the Typhoon Mindu in 2004, and when you have the flooding and then this huge sediment plume all around Taiwan due to the outflow of sediment from the island linked to the precipitation. And this can show why on Earth we have like a more important annual discharge of fluvial sediment is located in this area. Well, here it's obviously not exclusively Taiwan which is responsible, but Taiwan is a really significant contributor to sediment delivery on Earth. For example, so Taiwan is here, this small island, and actually this small island delivers the same amount of sediment per year that the entire United States. So a lot of sediment. And this allows to preserve clear identification of tropical cyclone. Here are the example of study we did on the Crenshaw formation. So it's only Pliocene where we have evidence sedimentary structure of tropical cyclone with multiple direction of trough cross bedding, coastal deposition of sandstone and mudstone, followed by cross stratification, and finally capped by mudstone. And we also have evidence using delta C13 on organic matter and the CN ratio to showcase that environment deposited in an average of 20 meters of water depths are exclusively dominated by terrestrial material. So what we did, we focused on the shoreline formation. So the shoreline is the youngest shallow marine formation in Taiwan, and we select this one as well because it's the formation that has the highest sedimentation rates in the of the island. So we focus on this one, and for those who know Taiwan, we went along the Holong River, like south to Miaoli, to log a 241 meters section. So here, what you can see on the picture is an overview of the shoreline formation with subvertical strata along the Holong River during a pretty sunny day, and this is the whole same river, same place, just after a small rain, and you can see like how much sediment is carried by the rain, and this was not even a typhoon, so you can imagine what happened during a typhoon. And another beautiful aspect of doing geology in Taiwan is like sometimes you have to make your own outcrop in the jungle. So now if we look more closely to the stratigraphy of the Holong river on the shoreline formation, so we have a strong cyclical pattern that occur with so the gray interval are more mudstone dominated interval, the yellow one are sandstone dominated interval, so we have a repetition between mudstone, sandstone, mudstone, and this pattern is occurring all along the outcrop with sandstone, mudstone, sandstone, mudstone, and so on, all around the outcrop. And this is not only a specificity that occur along the Holong River, but this is something that we can observe all across the island for the shoreline formation. Here's an example like in central Taiwan, like along the Wu River, where we have almost like 1 kilometer of thickness of the shoreline formation with a superb cyclicity preserved in. And here another example, like in between the Wu River and the Holong River with a strong cyclic pattern as well. So in order to understand deposition and environment fluctuations that we observed in the Olong River, we apply the facies model published by Nagel and collaborator, who did very detailed analysis of the interfall basin, and we use this model to constrain the bathymetry. So we use a simplified model constraining from nearshore environment and offshore environment. So for offshore environment, we recognize two main facies, the massive to laminated mudstone and the mudstone-dominated heterolithics that were deposited below 15 meters of water depth. And for the nearshore environment, we identify two main facies, cross-laminated sandstone and cross-bedded sandstone with thick mudstone bed and ribs. So this has been deposited above 15 meters of water depth. So here is an overview and a synthesis. So by applying this facies analysis and technology analysis, so we identify five facies with an extra one I didn't present yet, the biotubulated sandstone, which probably reflect reduced sedimentation rate during rise of the sea level. So here we have the nearshore environment, sandstone prone, cross-bedded heterolithics, here offshore mudstone prone, massive to thinly laminated. And therefore we have been able to identify 12 depositional cycle, which have an average thickness of 19 meters with the exception of C7, which is a 55 meters thick, but I will get back to this one later on. So based on the facies analysis, we first show like evidence of relative sea level variation from offshore to nearshore, offshore to nearshore, and so on all along the outcrop. So now we know that we have relative sea level fluctuation on the outcrop, but we need to know the timing about this fluctuation. So we use the formally developed magnetobiostratigraphic framework by Shen and collaborator, but we reassess for more accuracy the same interval, and combining both the former and our magnetobiostratigraphic framework, we can confidently say that our 241 meters thick interval represents 220,000 years, and that the individual duration of the cycle, except for the C7, is about 17,000 years in duration, and that we are close to the lower Matuyama Olduvai limit, so just right here, in a period that is supposed to be paced, where glacial cycles are supposed to be paced by the obliquity. So now we have our stratigraphy, our sedimentary interpretation, time constraint. So to pinpoint triggering mechanism of the depositional cyclicity, we compare our stratigraphy to an ice volume proxy. So we use a delta O18 from benthic foraminifera. We compare to an obliquity curve because it's expected to pace the glaciation during the early Pleistocene. And finally, we compare the stratigraphy to a P-0.5T curve, which is a very weird name for a mixed standard precession minus half-time standardized obliquity. So what I would like you to remember is like the P-0.5T curve. It's a precession-dominated curve. That's more important to remember for the rest of the presentation. So just a reminder, so the individual cycle are about like 18.7 meter, which theoretically represents 17,000 of duration. So we compare our stratigraphy, and when we look at the stratigraphy, there is one thing that pop out is that this cycle C7, which is the only interval in our stratigraphy that represents a relatively protracted low environmental variation. And when we compare to the other curve, the only pattern, the only interval and curve showing a low amplitude variability is actually the precession curve. So we decide to tie this cycle C7 to this low amplitude variability, which actually represents a long-term eccentricity minimum. So based on this, we continue comparing our stratigraphy to this different curve. And what's up here is like we have a best match with the depositional cycle with the P-0.5T curve rather than with the obliquity or the delta O18 curve. So this implies that when we have a minimum value of the precession curve, we have warmer summer in the northern hemisphere, and this led to partial melting of the northern hemisphere ice sheet, and this will induce rise of the eustatic sea level. So this shows that we have precession-dominated sea level change. But when we arrived to that conclusion, we were super happy, but at the same time, we were like, most of the studies say that obliquity is supposed to pace glaciation and then potentially sea level fluctuation at that time of deposition. So why do we preserve a precession signal in our stratigraphy? So this will probably deserve an entire presentation, but when we look to the movement itself of the obliquity and of the precession. So the obliquity will have an in-phase effect on the insolation receiver on the Earth. So it will increase or decrease. But because of the movement of the precession, it will have an opposite phase effect on the insolation received on Earth. Because when you increase the insolation on an hemisphere, you decrease the insolation on the other hemisphere. And this will lead to a preservation in the deep ocean of the delta weighting signal in the case of the obliquity. But in the case of the precession, it's like, see, there is a destructive interference. So that's why the delta weighting curve show almost no precession influence during that time, and in our case we show that in the stratigraphy we preserve that precession. So we underline the dichotomy between the shallow marine and the deep marine record. Now, another aspect I didn't speak on before, it's like our stratigraphy is not only composed by sea level fluctuation, but also our depositional cycle are compounded by extreme weather event. As you can see here, halfway up through shallowing upward cycle, we have sudden increase in sandstone, and this is unlikely in a regular shallowing upward cycle. So as you see at the beginning of the talk, Taiwan is strongly affected by tropical cyclone, and as you can imagine, is also influenced by monsoon. And when tropical cyclone and monsoon interact, we have an increase of the sediment supply at least by one order of magnitude. And just to show you an example, so in 2009, the typhoon Morocco impacted Taiwan, which was probably one of the worst tropical cyclone in terms of precipitation. It was only a category 1, but it was the more important precipitation, and only during one typhoon, a river from Taiwan delivered 700 megaton of sediment, which kind of almost represent the east part of the United States annually again. So when monsoon and tropical cyclone interact, the sediment is definitely increased consequently. And another aspect is like the monsoon is influenced by precession cycle, and tropical cyclone, which are temperature dependent, are also affected by the precession cycles then. So we infer that the sudden increase of sandstone in the offshore environment reflects the climax of tropical cyclone and monsoons that will increase then the sand export in offshore environment. But it is also kind of unlikely to preserve like high frequency events at such frequencies. So if we consider the source to sink environment, so for all climate perturbation occurring on land, the signal tend to be buffer when we have float plain that are greater than 300 kilometers. But the beauty of Taiwan is like probably all of the longest river in Taiwan is maybe about like 80 kilometers. So we have almost no floodplains that could tend to buffer and preserve the signal. So we have a direct source to sink relation in Taiwan that allow for preserving high frequency climate cycle in the shallow marine realm. So how do we tie all this together? So we developed a conceptual model of depositions that follow precession cycle. So when we have minima value of the precession cycle, we have warmer summer in the northern hemisphere that induce partial melting of the northern hemisphere ice sheet and rise in the eustatic sea level. and as well a minimum value of the P-0.5T induce higher tropical monsoon intensity and likely frequency that will increase precipitation rate and then sediment export. So our model starts with an initial phase here where we have a sea level low with sediment supply low and sandstone dominated nearshore environment. And then the insolation increase. So the sea level increase, the sediment supply rise as well. And we shift to mudstone dominated environment. And when we arrive at the insolation maxima here, we have the sea level, which is at the highest, the sediment supply is at the maximum, and the sandstone and the offshore shift from mudstone to sandstone dominated environment. And then when we go down in terms of insolation received by the Earth, we have the sea level fall, the sediment supply fall as well, and we turn to a mudstone dominated offshore environment to finally getting back to the initial stage with the sea level low, sediment supply low, and sandstone dominated nearshore environment. So from this presentation, I'd like you to remember two message, one on sea level and one on the sediment supply. So about sea level, what we show is that we have a strong correlation between depositional cycle and the northern hemisphere summer insolation, and that we have precession-dominated sea level variation in Southeast Asia during the early Pleistocene that contrast the general obliquity signal preserved in the deep marine record. And the other aspect is like we suggest that the climax of the tropical cyclone and the monsoon coinciding with the insolation maxima increase the sand content offshore. So when we get back to the rationale of the study, like testing the sedimentary recall of shallow marine with both high-accommodation and high-sedimentation as climate archive, yeah, it's definitely a valuable climate archive when when shallow marine environment are developed under this condition. And it's very likely that very outstanding climate archive must be discovered in the Southeast Asia, at least for the recent period of time, of course. And it's very likely that they should be like preserved in the small tectonically active island in this area of the globe. So with this, I'm ending my presentation. I would like to take the opportunity to thank all my wonderful co-authors without whom this study wouldn't have been possible. And I would like to thank also all the generous sponsorship of this study. So thank you for listening, and I will be happy to take some questions.
Thank you, Romain, for this very nice presentation with wonderful figures, wonderful pictures, and it was also a pretty express one. It was, you managed to do it very quickly.
Yeah, I told you, like probably like 35-30, something like this.
Yes, so we can still wait for a while until our audience is typing their questions into the chat. I'm pretty sure that there will be questions to you. I have to say from my side, I mentioned already, I really very much like all your figures. In particular, I think it was the model that you have showed. Yes. It was really very, yeah, very helpful.
Thank you.
Yeah, I liked it quite a lot. I guess that this is one of the big difficulties to work in systems like for the shallow marine system, when you have the influence of sediment supply, of the sea level change, and also of the, yeah, like subsidence, I mean, sea level change of the static sea level change. And so, yeah, I think you explained it quite well. I will most likely go to your presentation once again, once it will be recorded. Yes, this is an information to all of our audience that this presentation will be recorded, and you will be able to see it later on also on our website. And here we are starting with questions. So, oh yes, please, one last information. Once you're asking your question, please mention where you're watching this from. So first is from Tim Bryan. Very nice presentation, thanks. And right now, here comes the question, I guess. Yes, from Ross Campbell. Hi, Roman. Great talk. Thank you. So sandstone dominated offshore is due to increased storm events at phase of the cycle, at that phase of the cycle. And he's watching us from Ontario in Canada.
Okay. Yes, it's how we interpreted that shift in the offshore environment. When we have a shift to sandstone dominated environment, we interpret that it's the because like it's the cycle are not made like it was a classic parasequences with a gradual coarsening upward and gradual shift of phases. It was like really abrupt shift, like on off on the sand in the offshore environment, and so since we increase, we have the maximum export at the maximum of the insolation, so we carry the maximum of the material. So even if the tropical cyclone carried mostly muddy material, you have like a 10% of sand. So proportionally, you will bring more sand into the Paleo-Taiwan Strait. And at the same time, when you have an increase of the precession of the insolation, it's also affects the current pattern within the strait, which I didn't present here, but it will reinforce the export of the muddy material, so leaving more sandy material into the strait. So yes, we tie the maximum of insolation to the maximum of interference between monsoon and tropical cyclone, carrying more sand into the Taiwan Strait. Yes.
Thank you. Saikat from India says, very nice presentation. What is translation speed of the cycle? Why is it decreasing with global warming?
So the translation speed of the cyclone, so this is not the wind of the tropical cyclone itself, it's like how it's moving from land to sea, for example, not the inner motion of the tropical cyclone, but the lateral displacement, if you like, of the tropical cyclone. So now why global warming is tending to slowing down the translation speed? It's a good question. And from what I remember, it's because the global warming, it's somehow perturbing the atmospheric circulation, and this will lead to reducing the translation speed of the tropical cyclone. But it's way far from my knowledge to specifically telling you how the increase of temperature is really reducing the translation speed of the cyclone.
If I could help you here, Roman, very quickly.
Okay.
I remember that there was a paper in Geophysical Research Letters, I guess, from one of my colleagues from Newcastle University, dealing exactly with this phenomena. While right now, maybe not necessarily tropical cyclones, but why does atmospheric cells, which are bringing a lot of moisture, are right now simply staying longer over the continent, and they are moving slower over the continent. So this brings much more rain. And I think it was the paper, unfortunately, came exactly at a time when there was this very huge flood in Germany,
okay.
this late summer. So I can't unfortunately remember the name of my colleague from Newcastle University who published this paper, but generally, yes, she explained it really very well in her paper. But yes, I will just continue with more question to you. So from Stephen, our own Stephen Lockyer from England, great presentation. Sorry if I missed this. Is such a tectonically active region, do you rule out the effects of tsunami or tectonic uplift, subsidence, pulses, events? Yes, okay. That's a question.
Good question, Stephen. I'm not ruling this out. I mean, probably yes, there is definitely an influence of the tectonics on the sedimentation, but actually there is in the stratigraphic record and in the shoreline formation, there is two major disconformity, but I'm within this disconformity. So at least on the stratigraphic interval I studied, which actually represents a really small amount of time. It's only 220,000 years, as we do not have evidence of tectonic pulse, for example. And concerning the effect of the tsunami, yeah, at the beginning, good call, because at the beginning we thought we have like evidence of tsunami, but after when we read the literature and I look at the historical event of tsunami reaching the coast of Taiwan. So we are not on the east side. The east side coast of Taiwan is definitely impacted by the tsunami, but we are on the west side of Taiwan, and here we are kind of protected. So probably there was like some big wave, but from what I remember when I started this project, it was on my first call to look at tsunami deposits. It was unlikely to really have a strong impact of the tsunami on the west side of Taiwan.
All right, so yeah, thanks from Stephen. And the next question comes from Daniel Aristegui from Switzerland. Nice talk, Romel. I was wondering, why do you think that lakes do not record extreme events as mentioned in one of your earlier slides? Do you mean lakes in Taiwan?
Yeah, no, yeah, thank you, thanks, Daniel. Yeah, it was at the same time, should have maybe more precise on sea level fluctuation and in extreme weather at the same time. Obviously, of course, like lakes in Taiwan are definitely affected by typhoon each time there is one hitting Taiwan. So no, I was meaning at the same time, we do not have at the same time the sea level fluctuation and the tropical cyclone.
All right, so from Ross Campbell, again a question. Do you interpret the bioturbated sandstone as a deeper water deposit that is a storm deposit?
No, the bioturbated sandstone, actually we found two, the thick like 50, maybe like 50 centimeters thick, something like this. And no, we interpret them as low sediment deposition associated with like the sea level rise. That's simply like you have less sediment that allow for more bioturbation, and that's it. Maybe they are influenced by storm somehow, but it's not the way we interpret them, at least.
All right, thank you. And here comes the feared question from Stefan Baudin from Denmark. Thanks for the nice talk. Not sure to have understood you on the following point though. What do you mean by sea level, eustatic or relative? Do you imply that eustatic sea level fluctuations was paced by precession? In this case, how do you explain the obliquity paced Delaunay fluctuation?
But hi Stefan, good question. So when I refer to the sea level, I referred at the beginning, when I was only speaking about phases, I was speaking about relative sea level. And then after, when we tie that to precession, I was more speaking about a static sea level fluctuation. So we interpret that pacing by precession because it's actually the best match when you compare the pattern between the precession, the obliquity curve, and the stratigraphy. The pattern like just popped out, like there is no possible way to not see that correlation between the precession and the stratigraphy. And what I tried to explain, well, it was maybe not clear, but this yes, we do have a pacing of the delta 018 by the obliquity during the late Pliocene, early Pleistocene, but this is due to the motion of the motion itself between the obliquity and the precession. So since it's an in-phase effect of the obliquity, you will preserve that shift in the delta 018 with the obliquity pacing. And when you have the precession pacing, you will have an influence. It's just like you will have an interference between hemispheres that will cancel this signal. So I hope I answered your question, but if not, I will be happy if you want to discuss more after.
Okay, next question is coming from Victoria from Moldavia. Thank you so much, Romel. Your presentation was some. Quick follow-up question on the transitional speed of the cyclones and climate change. Given atmospheric warming, could there be a lesser contrast between cold and hot areas, thus slowing down the convection currents and therefore the cyclones too?
Yes, maybe. Let me reread the given. You will still, when you refer between cold and hot area, well, I assume you're speaking between equator and pole, so you will have less contrast between, but at the same time, since you will be like hotter, you will still create more tropical cyclone. I'm not sure, sorry, Victoria, I'm not sure I really get the sense of what you're asking. So if you, I'm sorry.
I imagine that this is exactly what you mentioned, that the tropics are still relatively hot, but the poles are getting warmer. So the gradient between the cold and hot.
No, the gradient will be definitely lower, and this may probably why you have an extent of the tropical cyclone up to the pole with the global warming.
Yeah, it looks like Victoria wrote that this is exactly what she meant. Yes, the cool. Tropics and the poles. Yes.
Okay. Cool.
So the next question is again from Psychot. This may be a silly question. No way, there are no silly questions. But how scientists measure precession cycle and correlate them to sedimentation cycles?
Okay, so the precession, I'm not good question actually. So no, there is definitely no silly question. If the measure, I'm not sure they are really measuring probably they are making some observation, but when we are using, it's more from mathematical equations that are developed by astrophysicians. So they are back calculate giving all the interaction between the planetary body in our solar system, because actually like eccentricity, obliquity, and precession are resulting movement of the Earth influenced by all the body, the planetary body around the Earth. So giving the mass, the distance, and their all rotation, they allow to create equations that we can use. And after the second part, sorry, what's it does move word correct. After, well, there is different way to match precession cycle in that case, or with the sedimentation, but you can do it with the eccentricity or the obliquity. So even you can do like pattern analysis. Like in our case, it was like obvious because like we have such a huge sedimentation rate that allow for a direct comparison between the cycle, the orbital cycle, and the sedimentation. On the other aspect, when you are dealing with more thinner and with more reduced sedimentation, for example, you can do like frequency analysis. So you analyze the data that you want to look at, maybe like, for example, the color, the gamma ray value, every proxy you want. And if you have an idea of the time, you can look if there is a frequency in the fluctuation of your data.
I see that Stephen added to our discussion on the contrast between the poles and the tropics that there's also a poleward expansion of the Hadley sail with increased CO2 concentration in the atmosphere. But now I will move to the next question, which is from Unai. Thanks for presentation, Romeo. It was fast and really on point. Oh, she's from Spain, or I'm sorry, or maybe he is from Spain. What's the average thickness of each of the precession cycle sediments? And regarding the sedimentation rate, is it constant for the succession or it changes through the time with sea level fluctuations?
What we measure, it's like we have an average thickness. It was like 18.7 meter for each cycle we measure, but this is only like the measure on the outcrop. And regarding the sedimentation rate, constant. Probably, well, there is some fluctuation, but we cannot. What we can infer as a fluctuation of the sedimentation rates is like when we tie each cycle to maxima or minima. So the precession cycle are having basically the same interval, but when we compare to the stratigraphy, sometimes we tie them to more thinner or more larger depositional interval. So definitely this is somehow highlighting sedimentation rates fluctuation. But yeah, of course, the sedimentation rate is it's not supposed to be constant during all the deposition, but we cannot really know how what was the fluctuation. We have a really good time constraint, so we minimize somehow the uncertainties about the sedimentation rates, but yeah, there is definitely some sedimentation rate fluctuation.
Next question is coming from Sarah from New York. Great talk. An interesting addition to test your conclusions could be to take a look at the detrital circon grains composition rounding in your neutral faces. I would expect a unique signature to appear in those facies after a cyclone event, which could add to your argument for an insolation correlation. Do you plan to look at any features in the facies to add to your conclusions?
Good question. No, I already asked question about fragment analysis, yes, but I didn't think like to look at specific for the sandstone-dominated offshore. But yeah, no, it's something I didn't think about, and I think it could be a great value to add on, and I would definitely consider it. The only thing, like I need to be allowed to go back to Taiwan because the borders are still closed. So yeah, my fieldwork is still on pause. So yeah, but good point on that. Thank you.
Right, so we have more thanks from our audience, and I think that with this we can slowly close the discussion. Also, please remember next week, so same time, same place, basically, at 4, and the talk will be given by Daniel Aristegui from the University of Geneva, and I think he will be talking about microbes and lacustrine carbonates, the good, the bad, and the ugly. I have to say I really like the title, and I look forward to this talk. And Romain, thank you very much again for a very inspiring talk full of nice figures and nice pictures. And thank you, dear audience, and I guess see you next week.